Okay, without further ado. So our next speaker is Angel Ruiz. He's joining us from Athens, and he's going to be telling us about using BXA with some XMM-Newton data. So over to you.
Thank you. Okay, can you hear me? Fine. So yeah, I'm going to present this work that we did in the National Observatory of Athens. It's along the lines of 10 talk with Rosita, but with the just in this case, the 3 XMM-Newton catalog, you know, the serendipitous surveys from XMM. And the particular thing of this is that we try to use photometric redshift information using including within BXA. So why is not? Okay. Well, okay. So in the National Observatory of Athens, we've been involved in several projects of developing what we call value-added catalogs to the 3 XMM, 4 XMM, whatever. And all this started with this XMMFITCAT. It was a catalog of spectral fits for all sources in the 3 XMM with spectral data directly from the archive, with some quality cuts in for the analysis in the spectra. The problem with this catalog is that it doesn't include redshift information. We have no idea of the distances of the sources, so we have estimation of the fluxes, estimations of NH, but are not very informative. I'll speak a bit more about that. So our next step was to build this catalog, XMMPZCAT, that we try to calculate photometric redshift for these X-ray sources using, I'll go into more details later. And then combining what we learn and what we should avoid doing with this catalog and the information from this, we build the XMMFITCAT-Z. Yeah, we have to think a bit more about the names of our catalogs, but well, that's different. And this catalog contains a spectral fit for around 30,000 X-ray detections. And this was built using BXA and including the photometric redshift from the previous catalog. And all this catalog, you can find it here, you can download it. This one is also included in VCR, so you can go there and play with the data if you want. So let me tell you a bit more about our catalog of photometric redshift. This is a catalog of 100,000 sources for the 3 XMM, and we include only sources above the galactic plane to avoid, we were interested in extragalactic sources, so this way we cut a lot of the contamination due to stars in the galaxy, essentially. And what we use for the photometry to calculate the redshift was these two catalogs in the optical, the SDSS or PanStars. And when it was available, we use near-infrared data from the TUMAS, UKIDS, or VISTA, and mid-infrared data from Allwise. And we did our own cross-matching of all this catalog using a statistical cross-matching using XMatch. That is a cross-matching tool developed by Jean-François Pinault and others for the ARCHIS project. And what the technique we used for the photometric redshift was using the random forest technique with regression trees. And essentially it's this MLC TPZ software that is pretty well tested, and it works pretty well for machine learning estimation of photometric redshift. And our training sample to calculate this redshift was based on 5,000 X-ray sources, which is quite a few compared when you see this kind of work before for optical sources that they use training samples of millions of sources, but this is what we have in X-rays. So, and some of the results, this is a comparison of the photometric redshift we estimate against the spectroscopic redshift for sources that have both in the catalog. So you see that in general agree pretty well. You can see in more detail the results here for different, depending on the photometric bands that they were available for the sources. This sigma is essentially the dispersion, and eta is the fraction of catastrophic outliers. I mean, when the source falls outside this central region. So essentially, what you can get from all this is that when you have a lot of photometry, you can calculate pretty good photometric redshift for X-ray sources. When you have only optical information, things doesn't work so well, particularly when you go to point-like sources that you get 40–30% of outliers. But when you have enough photometry, things work reasonably well. So this is about the XMMPZCAT, XMMFITCAT. As I said, this is spectral fields for 3 XMM. It's an automatic process for spectral fitting. We fit almost 160,000 detections, for each source, analyzing the PN and most data available for each detection. And this was done in the traditional way, using a cast W-stated statistic with XPEC, using a standard Levenberg-Marquardt minimization algorithm that we talked about this yesterday. And well, this makes your life very complicated. And among other things, we have to fit in 3 different bands because this problem, essentially, the local minimization when you fall into a local minimum. So you have to try in different ranges to be sure that you are not falling into a local minima. So that way it was a way of avoiding that. But so yeah, I can here essentially we use 6 different models. These 3 simple models, that is an absorbed power law or an absorbed thermal emission, a mecal or a black body. And then for when we have a spectra with enough counts, we try more complex model like absorbed power law with thermal emission, a double power law with different absorbers, or again a power law with black body absorb. And here is a comparison between the fluxes that comes directly from the 3XMM catalog and what we get from our fit. So you see that in general they agree, but you have some dispersion, when essentially because for the calculation of the flux of the 3XMM, you assume a certain spectral shape. When the spectral shape is not what they assume, you get differences. So in general, the fluxes that we calculate here are more accurate because the phenomenological models that we use here, they cover a broad range of spectral shapes. So in general, it works very well. And what I was saying, this work, the main issue is that you don't have distant information. The physical parameters that you get here are not very informative, to say the least. For example, if you have an NH of 10 to the 22 means nothing because if the refs is high, it could mean. So yeah, you can have an idea if the source is absorbed or not, but you cannot gain much information from that. And obviously, you cannot calculate luminosities. What I'm saying, doing this with a traditional fitting method is a nightmare. Because you see the code that it was developed to do that, And this was started in 2012, 2013. So at that time, there was no PyXspec. So scripting in spec is a nightmare. And all this code was collection of 29 scripts in Bash, TCL, Perl, whatever. And most of the code is essentially trying to avoid and test if you are in a local minimum or not. And the other half of the code is how to deal with error estimation and edge cases when you are in the border of the interval. It's a nightmare. You can do it, but the initial idea is very simple, but the moment that you are going into the different tests, the code grows into an spaghetti nightmare. So when we wanted to do the same, apply the same idea, but bringing this photometric information for this catalog, well, I complained a lot to my boss, and I said that we should use BXA because it was going to do our lives much easier, and at least for me it was. Because, you know, so the idea was to do automated spectral fits for 30,000 sources. So there were sources within the photometric redshift catalog and with a good quality index spectrum, at least to have 50 counts in. So, so then the selection criteria was the same for this catalog and the previous one. And as I'm saying, we use SERPA, in this case, no XSpec, for the same reason. The PySpec module didn't exist yet, so scripting with SERPA at that time was much easier, and adding the BXA. BXA with multiness, it was the version 3, not the version 4, so ultraness was not released yet, so we use it with multiness. And the good thing of using BXA is that we could include the whole information of that we gain in our photometric redshift calculation directly. We didn't need to do any estimation. I'll explain later what I mean with that. So say, why BXA? Is what Johannes was saying, for example, this morning. Having a method to do a global exploration of the parameter space, you know, makes you sleep better at night because you're having nightmares of being in a local minimum. And for a project like that, where you cannot go spectrum by spectrum checking if the fit makes sense or not, having an automated algorithm that do that is really useful. And by that, we can skip doing fits in 3 bands. We can use just a single band fitting in the spectral range of interest. As I was saying, you have a tight control of the parameter priors. You can control very well your priors, and particularly for the redshift, allows you to include that information in the prior. And what we've been hearing all day, we have full posterior probability distribution for the parameters, and there are quantities like fluxes, luminosities, etc. It makes your life easier when you try to do some kind of error estimation, as far as your distribution is monomodal. When you have bimodal or more, things get a bit complicated, but at least you have the posterior. You know how things are, and that's really useful. And the other thing is we did this in Python with SERPA and everything, and the code now is something that you can look at. So this is, for example, 3 examples of sources with the 4. In this case, we use 4 different models. These 2 simple that we apply in all cases: an absorbed power law and an absorbed thermal emission, a MECAL. And these 2 more complex models were only applied when you have enough counts for the spectra, like above 500 counts. So you see that in general, the results are actually quite good. Let me show you some more examples. These two are highly absorbed sources with you see I mean, this is the spectral data. The red line is the the source plus the background emission, and the dashed line is the source model. And you see, since you have the posterior distribution of the parameters, you can actually calculate the confidence regions for the model in the plot of the spectrum, which is quite nice. And this is another source, the same. And here is the distribution of the parameters. This is a simple absorbed power law, you see, with NH very close to 10 to the 24. And this one is 10 to the 23. This is a double power law with two absorbers, the gammas, the redshift, and the NHs for the two absorbers. So this is a comparison between the again with the fluxes and our calculation of the fluxes, and this is the luminosity versus redshift. And here you can see something that is not very that is that you find a lot of well, not a lot, but significant number of sources with a very high luminosity in the hard band, about 10 to the 47, which it really doesn't make a lot of sense having such huge luminosities. And this is essentially a case of you know, this complex model that I showed you before. You know, they are purely phenomenological, and sometimes, you know, they have overestimation of the NHs, when you calculate the intrinsic luminosity corrected by absorption, gives you unreasonably high luminosity. So if you go carefully through your results and filter out those weird cases with unreliable results for the modeling, you get a luminosity distribution like this without no high luminosities above almost 10 to the 46. So this is, you know, the problem of doing automatic things, that sometimes you assume things that are not physically, or, you know. So the best that you can do is, as Teng was saying, all the models are wrong, some are useful. And yeah, when you want to do science with this kind of catalog, you have to be very careful. You have to understand very well how things are done and select things properly to take into account the possible issues. So, okay, so the thing about the photometric redshift. So why actually we're interested in using BXA for this? Essentially because, you know, sometimes you have a photometric redshift. This is the probability distribution. You have something nice like this with a narrow peak. So in this case, you could say, okay, usually when you use redshifts in a spectral fit, you assume that it's a fixed parameter because the uncertainty is small compared with the uncertainties of your data. So you can live with that. But with photometric redshift, that's not the case. The uncertainties of photometric redshift are significantly higher, and particularly for X-ray sources. So, but still, you know, if you have a probability distribution for your redshift like this, okay, you can say, okay, let's use a Gaussian with a certain width, and we can approximate like that, and that will be your prior. But what happens when you have two peaks? And this is very common in photometric redshift. You have estimation when you have some dominant value, but it's not negligible, no? the other solution. And in these cases are more or less closer, but sometimes they are quite separate. So you need to find a way of maintain. I mean, we want to maintain this this bimodality in the redshifts, because why not? I mean, it's what your solution is. So why you shouldn't choose one and forget about the other. If you can keep that information all along your fitting process, it's a much better thing to do. And sometimes you simply have something awful like this, where there is no clear solution. The probability distribution is very broad, but still, I mean, a very sensible decision would be, okay, let's forget about this and not use it in the fit. But well, this is what you know about the redshift. You don't know much, but this is what you know. So why not use this little information that you have instead of forgetting about the source? And also, my boss cries a lot every time that we remove a source from the catalog. So if we can avoid that, it's better for us. And so then, since you have a probability distribution, in our case is a simple tabular function for redshift against probability. So using this as a prior for BXA is trivial. So I mean, in BXA you have some predefined priors like a flat prior, a flat Jeffreys prior that is flat in the log scale. You have Gaussians, but you can use whatever function you want. Essentially, a prior is a function that the input is a number between 0 and 1, and the output is a value for your parameter. So if you want to reproduce the the probability distribution, it's the typical thing. Is the inverse, is the inverse of the cumulative distribution. From this, you can calculate the cumulative, and then you do the inversion, and you plug that as a prior, as a function, as a definition of the prior function, and it works. And the output is, if you run that, the output of the prior is this. I mean, the code is very simple. If you are familiar with Python, it's very simple to do with NumPy. But still, I mean, if you are interested on knowing the details on how to do this, just ask me. I'm going to be around. I can show you the code if you want. It's very simple. It's 3 lines. So that's why I'm not going into much details. But okay. So that's the main reason. And so what happens when we use that? For example, here on the right, you have you have this kind of redshift distribution with 2 peaks, and you see how this bimodality is propagated to different parameters. This is the normalization of the of the power load, and you see how the bimodality is also propagated in the NH. And or in this case, this is an example of a different source. You can also see that here, this is the redshift. You have almost 3 peaks, and how they are propagated, for example, here in the normalization. So, you know, by using BXA and keeping these priors, this information is propagated along the parameters. And the problem, you know, when you do these kind of things, and you build a catalog and people want a number and an error interval. And yeah, when you have bimodality, that kind of things doesn't make a lot of sense. So it would be nice if we could find a way of actually, you know, distributing the probability, the full probability distributions in the catalog instead of doing this sort of calculations. But at some point we will do it. So just one other thing about photometric redshifts and how to deal with their probability distributions. You know, usually the output of a photometric redshift code is just, you know, the kind of thing that I showed you before. The problem there is that there are other systematics that you can introduce in your PDF and use that as a prior for the thing. And this is an idea of also of Johannes in this paper of 2015, and it's how to modify your probability distributions, taking into account the intrinsic dispersion and the probability of having a catastrophic outlier in your data. Essentially, it's correcting the PDF. You know, it's a convolution of the PDF with a Gaussian with this with this dispersion, and then a constant prior based on the probability of being an outlier. This is how you correct your initial PDF to the final PDF that you want to use. And then you can see here 2 examples. This is from a paper of Hector Aspouliasis that is around. And we use this idea to correct the probability distribution of redshifts. And you can see how the output of the code gives you very narrow, it's bimodal, but narrow peaks for the redshift. But when you take this effect into account, you have more broader and also a not null probability of being within the range. So it's something to have in mind if you want to use photometric redshift to take into account this kind of effects. What else? And yeah, just to finish, well, also, if you are interested on the details on how to do that, I can show you the code and explaining how to do it. So just to finish, a couple of things that I'm working on also with BXA. One is this project of doing X-ray spectral analysis of sources in the XXL, particularly for high-res sources. This is something that Hector and me we are working on. And the interesting thing here is what Johannes was saying this morning. It's about using BXA when you have very low counts. You have a spectra with very low counts, because in high redshift, XXL is a relatively shallow survey, and we are trying to do a spectral analysis for every source. So yeah, sometimes you have very faint sources that are background dominated, but you can extract a lot of information sometimes from that exercise. The most hard part is actually convincing people that thing works. but it's an interesting. There are interesting results there. And the other thing is XMM to Athena. This is a collaboration between several European institutes, and it's how to learn things from analyzing XMM data to apply to Athena, the future European X-ray mission. And there are many things that many institutes and many things that we are doing here about source classification, photometric redshift. But one of the things is, repeating our exercise of automatic spectral fits for the 4 XMM catalog in this case, and again using BXA. And in this case, the work is being led by Santander, Instituto de Física de Cantabria in Spain. But yeah, essentially we are using a new version of the code that we use for the catalog that I presented. And that will be all. Thank you.
Yeah, thanks very much. It's a very interesting talk. Do we have any questions in the audience, first of all? Anyone? No. Do we have any online?
So yeah, Martin Topinka was actually wondering if any of the scripts for generating your beautiful plots are available somewhere, maybe perhaps on GitHub or something like that.
Not yet, but you can contact me and we can.
Great. Okay, thank you. That's it.
The one that they are physical, the one that you said they are physical. I was wondering that, yeah, when you go to Z, so you're saying that when they go around 10 to the 47, is that obviously the intrinsic? Is the intrinsic luminosity? Yeah. So because the fact that some of them are more luminous around like 1 or 2. I mean, in that period, obviously, in the cosmic time, I think the quasar phase is really, really important, and therefore are more luminous. Did you take into account that in a sense that, or for you they are completely, I mean, over 10 to the 46 are completely unphysical? I mean, okay.
To actually go into the spectral models of those high luminosity sources and understand what's happening there. I mean, if this result makes sense or not. And in most cases, what you see is that these sources are coming from complex spectral models. And you have, for example, a double power law. And essentially what you see is that you are mimicking, like, for example, for high redshift, you are mimicking like the quantum hump that start going into the thing with a very absorbed power law, just because it's trying to do that. So, and when you see that, they say, okay, this kind of model is not physical. It's not going into that. So essentially, for example, what we want to do for in XMM to Athena is to avoid this kind of purely phenomenological models and try to use, I don't know, for example, a proper physical model for AGNs, like a torus, so that way we can avoid this kind of things.
So yes, I was curious. I mean, this might be partly more of an advert for another talk we have later in the week by Charlotte. But you spoke a lot about photometric redshifts. I was curious if there's any plan to maybe use in particular the absorbed sources that are found, whether you can somehow use BXA to reverse engineer a posterior on the redshift, say from the edge at around 6 keV or something like that.
That's something that I always wanted to do, like since we have a very large catalog, to do a statistical analysis of how your spectral data modifies your prior in the redshift. Something that I wanted to do, but I never got the time to look with that in detail. But I know that other people have tried to do that. And in general, what you see is that when you have a highly absorbed sources with a clear absorption edge or a strong emission line, you can find redshift directly from the X-ray data. But in the general case, when you only fit the continuum, it's very hard. But yeah, still, I would like to search for these cases here, but I never got into it.